admissibility of a generalized Bayes estimator. So this is a very general result, again like the last one. So suppose theta is a subset of Rk is open. For any, so that is the first condition. For any delta, so which is same as condition this, that R delta theta is a continuous function of theta. For any delta belonging to D with R delta theta as finite for every theta, R delta theta is a continuous function of theta. Third, here what I was saying was, because here I had a fixed prior, there exists a prior pi and a Bayes estimator corresponding to this. So here what I have doing is this delta which is given to me. So I am given a delta which is in limit a Bayes. So that means there exists a sequence of priors which can be generalized improper priors, pi m and an estimator delta naught such that what happens? Just to be mathematically precise, let me write down limit infimum of R delta naught pi m, so that means Bayes risk of delta naught, minus R delta pi m, so this is a Bayes risk of a Bayes rule with respect to pi m, divided by pi m b is 0 for every open set B. Of course, open set B not equal to phi, because empty set is always taken as an open set. So wherever I am talking about pi b is positive, that means for every non-empty open set B, even in the last theorem. Then if such a thing happens, there is a no Bayes rule over here. This in certain sense is suggesting that, you see, in general R delta naught pi m would be greater than or equal to R delta pi m, because delta pi m is Bayes. So its Bayes risk is smallest. So that means this would always be greater than or equal to this. Now if in limit this is turning out to be 0, so this gives an indication that in certain sense delta naught is a limit of the Bayes estimators. Now it says if that is the case, then delta naught is admissible. So what this theorem suggests is that not only the Bayes rules are admissible, limit of Bayes rules, limit in the following sense, that means the limit in the Bayes risk tend to 0, or in limit of the Bayes risk of delta naught, in limit goes to the Bayes risk of the Bayes estimator. If that happens, then delta naught is admissible. The proof more or less is on the lines of the last theorem. So I assume that delta naught is not admissible or delta naught is inadmissible. So that means on contrary, suppose there exists a delta star which is equivalent to assuming that delta naught is inadmissible. So there exists a delta star belonging to D such that R theta R delta naught theta is always less than or equal to, R delta star theta, because I am assuming delta naught to be inadmissible. R delta star theta is less than or equal to R delta naught theta. for every theta. And there is a strict inequality for some theta. As usual, I have to use this continuity, so I construct a set So first I take r delta naught theta naught minus r delta star theta naught to be epsilon, because that is positive. So r delta naught theta naught minus r delta star theta naught is epsilon. I take B to be, as in the last theorem, collection of all those thetas in capital theta, such that r delta naught theta minus r delta star theta is greater than epsilon by 2. Then suddenly B is non-empty, because when I put theta naught, this quantity is epsilon, which is bigger than epsilon by 2. So B is non-empty. In fact, theta naught belongs to B. Second thing, what is this? This is a continuous function. Because for any risk function for which risk is finite, here risk has to be finite. You can easily see, otherwise there will be issues here itself. So it is a continuous function, so it is a inverse image of this difference function of inverse image of epsilon by 2 to infinity, open epsilon by 2 to infinity, under this difference. But this difference is a continuous function, and you know that for a continuous function, inverse image of an open set, which is epsilon by 2 to infinity, is always open. So B is open. What does that mean? Pi of B is positive. I now consider r delta naught pi m minus r delta pi m pi m. I do exactly what I did last time. So this is theta r theta delta naught minus r theta what I have done is, so what I do is I consider this, but delta pi m is base, so its base risk would be less than or equal to base risk of delta star, so this would always be greater than or equal to r delta naught pi m minus r delta star pi m. Why? Because delta pi m is base. So r delta pi m would be less than or equal to r delta star pi m. So here with a minus sign, you get a greater than or equal to. And what is this? This is nothing but integral over theta. This is the average of the frequentist risk. So r delta naught theta minus r delta star theta d pi m theta. I break it into two integrals as we did last time, B and B complement. Now note that by this property, r delta naught theta minus r delta star theta, r delta naught theta minus r delta star theta is always greater than or equal to 0. So this quantity is always greater than or equal to 0. I break it into two parts, B and B complement. So certainly in B complement also integrand is greater than or equal to 0. So this would always be greater than or equal to integral over B of so this would always be greater than or equal to integral over B of r delta naught theta t pi m theta. But on the set B, this quantity is always r delta naught theta minus r delta star theta on the set B is always greater than epsilon by 2. So this is always greater than equal to epsilon by 2. So that means this whole quantity is always greater than equal to epsilon by 2 times pi m p for every m. So what do you get? You get r delta naught pi m minus r delta pi m divided by pi m b is always greater than equal to epsilon by 2 for every m greater than equal to 1. There is no m over here, there is only m over here. So I can take the limit. Just to be mathematically precise, you know that sometimes limit may not exist. But limit doesn't exist, that's not a big issue, because if limit does not exist, you know that limit infimum and limit supremum always exist. So if you have a sequence am such that am is greater than or equal to some constant c, so if am is greater than or equal to c, that means limit infimum am is greater than or equal to c. On the other side, if am was less than or equal to c for every m greater than or equal to 1, you could have said limit supremum of am is less than or equal to c. Now in this case, since this is a sequence which is greater than or equal to epsilon by 2, this implies that limit infimum and go to infinity of r delta naught pi m minus r delta pi m by pi m b is greater than or equal to epsilon by 2, which is greater than 0 because epsilon is always positive. But what is given to you? That this limit infimum has to be 0. What you have proved is limit infimum is always greater than 0. So I get a contradiction. So this implies that delta naught is admissible. So very nice. So what we have done so far is, so under certain conditions, a Bayes estimator is always admissible. That was the first theorem which we did. And what are those conditions? If your Bayes estimator is unique Bayes, it would be admissible. If your prior distribution is such that it gives, such that for any countable theta, that means your parametric space is theta, and your pi gives a positive weight to every element of theta, then Bayes estimator is admissible. Then we also saw that Bayes estimator is admissible provided your risk function is such that it is continuous function of theta for any decision rule delta, and your prior assigns positive weight to every open set, then also it is admissible. Then we saw that this theorem can not only be extended for the Bayes rules, but it can also be extended to the case of generalized Bayes rules. And we saw that even when you have a certain estimator which is a limit of a Bayes in certain sense, so limit of a Bayes in this sense, then also such an estimator would also be admissible. Now note that this result is slightly stronger than the part C of last result, because if you take all pi m's to be pi, all pi m's to be pi, and delta naught to be delta pi, then this condition is always satisfied. And that says that delta pi is admissible. So this result is general than the part C of last theorem. By choosing pi m's to be pi itself, a constant sequence, and delta naught to be delta pi itself, the Bayes rule itself, because then this condition is always satisfied. Because delta naught is delta pi, so delta pi pi, delta pi pi, which is always 0 for any open set, even if you divide it by pi of b. Pi of b, so pi of b is positive. So it is more general than the last result. This is also true for generalized, for improper priors. Okay, now the question arises, I have assumed that this result will be a valid, even the following result would be valid, if your risk function is a continuous function of theta for any decision rule delta. How restrictive is this condition? Now, if you recall, while doing testing of hypothesis in your last course, you must have done a result for the one parameter exponential family or even a k parameter exponential family, where you proved not only the continuity, but the differentiability of expected value of any function psi for which expectation is finite. So in exponential families, this condition will always be satisfied. So there is no issue. So exponential family means like normal, gamma, exponential, binomial, Poisson, and so on. So let me formally write down that result. In fact, the result follows is a simple applications of your dominated convergence theorem. So let me write down that result so that you are aware that this assumption of continuity of risk function is not too restrictive. It will always be satisfied whenever you are dealing with a exponential families of distribution. So let me write down this theorem. So suppose f theta, theta belonging to capital theta, this is a family of PDFs or PMFs, depending on whether your dominating measure is a Lebesgue measure or a counting measure. And suppose f theta x is same as e to power summation I is equal to 1 to k tix theta I minus xi of theta into h of x where of course you know xi theta comes through the normalizing constant, right? So let me not write down that. So xi theta is certainly, if it is a PDF, then xi theta has to come through normalizing k. Now if theta naught is an interior point of theta. So that means if theta itself was open, then theta naught could be any point of theta. And psi is such that expected value of mod of psi x is finite, then E theta of psi x, which is nothing but integral over rk psi x, f theta x dx is finite. So psi is a real valued function, right? So psi is from rk to r. So such that expected value of psi x, no, so what I am assuming is that E theta naught at the interior point theta naught expected value psi x is finite. Then this is infinitely often differentiable. In a neighborhood, so NBD means neighborhood of theta naught. So that means there would exist an open interval around theta naught such that this quantity would be differentiable infinitely often in that open interval inner neighborhood of theta naught, and the derivative can be evaluated by differentiating under the integral sign. All right, so for any function psi which is real valued, if expected value of psi x is finite, then expected value of psi x can be differentiated infinitely often. Now, normally this derivative would be sitting outside the integral sign. He says, but you can take the integral, this derivative inside the integral sign. So that is what it says, and the derivative can be evaluated by differentiating under the integral sign, and you can differentiate it as many times as you wish. So exponential family, this continuity of a risk function is not an issue at all. So you can blindly do that. But let me just make a small comment over here. You see, normally there should be a range of theta. So here range of theta is collection of all those thetas such that, so my parameter space is nothing but collection of all those thetas such that this xi theta is some sensible quantity. That means this should integrate out to 1. So this is same as integral over e to power summation ti xi dx hx is finite, right? So which is equivalent to saying that e to power xi theta would be a finite quantity, and you call this as a natural parameter space. So in a nutshell, what this theorem is trying to convey is that, look, you can blindly apply the last two theorems if you are dealing with the exponential family. Continuity of risk function is not going to be an issue because of this. In fact, you have much more than continuity. You have differentiability of any risk function. Now let me do one final result for today, which basically says that if you have a Bayes rule, it will not be unbiased. So that means any rule which you get as an unbiased cannot be Bayes with respect to any prior. So let me do this result. So delta naught is Bayes estimator of g theta with respect to a prior pi under the square error loss. So you have a estimator which is Bayes under the square error loss with respect to some prior pi. Then the Bayes risk of delta naught pi has to be 0. How do you prove this? Very nice result, and it's very often used to show that a certain estimator is not Bayes. So how do you prove it? So delta naught is so let's look at R delta naught pi. It is expected value of average of risk. So this is same as expected value with respect to S of L S risk, right? R S delta. Actually, risk you are writing down as R delta S, which is same as expected value of S. And what is R delta S? This is the frequentist risk. So this is same as expected value of x given s of L s delta x. Now, one thing you should note is, what is your delta naught? Under square error loss function, the unique Bayes estimator is nothing but the posterior mean, right? That is what we saw. In the case of square error loss function, the Bayes estimator is unique. Not only it is unique, it is given by the posterior mean. So, our delta naught x is going to be posterior mean, so that means expected value of s given x of s. Right? That is what we have already seen. Now, let us try to see what is this expectation. This expectation of a conditional expectation, so this can be written as joint expectation, and joint expectation can further be written as expectation of a conditional expectation. So, R delta naught pi can always be written as E of x and E of s given x, right? Because if you look at this expectation of a conditional expectation, this is a total expectation. Now, total expectation can be further written as an expectation of a conditional expectation, except that the orders of expectations have changed. So, here I am talking about expectation of a conditional expectation. Now, the conditional is with respect to s given x. Earlier it was with respect to x given s. Okay, loss function I already know is nothing but delta x minus, so s minus delta x whole square, because we are talking about square error loss function. So, what is that? That is expected value of x, expected value of s given x of s square minus 2 e of x e of s given x of s times delta x plus e of x into e of s given x of delta s given x. Now, let us consider this quantity. Actually, to begin with, it was better that there is no need to write down conditional expectation to begin with. You can write down just E of s comma x, total expectation, so that you don't have to carry double expectation all the time. So, E of s comma x. Conditional, I'll write down wherever it is required. Otherwise, why to carry these E of sx, and here also. So, what I will show is, I have to show that this is 0. I will show that one of this gets consumed with this, one of this gets consumed with this. So, let us consider. So, let me just write down the statement. Actually, I have written down, if delta naught is Bayes estimator of g theta and is also unbiased. So, what this result says is, if you have a Bayes estimator which is also unbiased, then the Bayes risk would always be 0. Or in other words, if you have an estimator for which Bayes risk is positive, then it cannot be unbiased. That is what it is equivalent to saying. So, that means this result can be used in proving that certain Bayes estimators are not Bayes. In fact, generally this condition will not be satisfied, because this would be an average of some non-negative quantity. So, average of non-negative quantity would be 0 only when your either prior is such that it gives weight to only one point. So, except in trivial cases this would be satisfied. So, except in trivial cases your Bayes estimator would be unbiased, otherwise it will be a biased estimator. So, now let us try to see expected value of Sx of S and delta x. I first write down this as two conditional expectations. So, I will write down this conditional expectation of a conditional expectation in two different ways. So, first I write down E of S, E of x given S, S delta x. Actually, what I was interested was not S. I was interested in estimating g of theta. So this would be g of s, right? Everywhere. So this would be g of s because loss function is square error and you're estimating g of s. So this would be gs square. This would be g of s. So I consider this quantity. Yeah. So estimate is not theta, but g of theta. Okay. Now what is happening is here s is constant, so that goes outside. And E of x given s of delta x. What is this quantity? Delta is unbiased for g of s. So what does that mean? This is nothing but E of s. Sorry, this would be g of s again. Am I making, yeah. So this itself is g of s. So g of s becomes g square s. And that is what was happening. It was 2 times, so one of this will get absorbed with this and become 0. Secondly, I'll again write down this as an expectation of a conditional expectation in a different way. So E of Sx g of s delta x. Now I write down this as E of x and E of s given x. And now note that this is joint expectation, but there is no s is coming, so this is same as Ex of delta s square x. Similarly, here it is a joint expectation, but there is no x over here, so this is only expectation with respect to s. So E of x, E of s given x of g of s delta x. Now what is happening over here is now outside integral x is there, here x is fixed, so delta x goes outside. And then E of s given x delta x. Actually, this delta x would be delta naught x, right, everywhere? This small slip in notations everywhere. So this would be delta naught. Right? There is no delta. But what is this quantity? Sorry, this would be g of s. Delta naught x is gone outside, so this would be g of s. But what is this quantity? Because you are dealing with a square error loss function, so your base estimator is nothing but a posterior mean. And this is nothing but a posterior mean of gs. So this would be delta naught x as we have it over here. So this gives me, so this is same as Ex of delta naught square x. So there was 2 of this. One of this gets consumed with this. One of these gets consumed with this. So this implies that R delta naught pi is 0. So what it says that if you have a base estimator whose, sorry, if you have a base estimator which is also unbiased, then the base risk of delta naught has to be 0. But that will never be the case except in trivial cases. So what does this suggest? This suggests that base estimators will always be a biased estimator. A base estimator cannot be unbiased in natural situations with respect to any prior. So for example, when you are dealing with a normal case, x1, x2, xn, IID normal theta 1, x bar I know is unbiased. So if it has to be base with respect to a prior pi, then its base risk would be 0. But what would its base risk? Base risk would be the average of the frequentist risk. Frequentist risk of x bar is 1 by n. Average of 1 by n would be 1 by n, which will never be 0. So immediately you conclude that if you have a sample from normal theta 1, then the UMVUE, which is x bar, cannot be base with respect to any proper prior. So I cannot conclude admissibility of X bar using the two results which we did, saying that continuity of risk function result. But we'll see that X bar, in fact, in the normal case is admissible. So we'll have to use possibly the second result, where X bar, although it is not Bayes, can I say that it is a limit of Bayes in certain sense? So that all we'll discuss next time. So that's all for today, and thank you for your attention.